gain margin and phase margin are the two performance parameters which are helpful to know the stability of the system. So, in a control system, gain margin is defined as the amount of gain that can be still added to the system without affecting its stability. So, these two, gain margin and phase margin, can be determined from the polar plot, where polar plot is the frequency response plot. It is like it consists of concentric circles and radial lines. So, concentric circle represents magnitude and radial line represents phase angle. So, the plot can be drawn in polar graph sheet, or plot can be drawn on ordinary graph sheet. So, when you want to draw the polar plot on ordinary graph sheet, the polar coordinates must be converted into rectangular coordinates. So, it consists of real and imaginary terms. Originally, the polar plot, it consists of angles 0 degree, minus 90, minus 180, minus 270. So, the measurement of angle on polar plot in clockwise direction in this fashion, and if it is counterclockwise direction, then the angles are plus 90, plus 180, plus 270, and so on. So, this is for counterclockwise direction positive angle and clockwise direction negative angle. So, for a particular problem or system, if the polar plot is in this fashion, as the omega is increased from 0 to infinity, frequency in radians per second is increased from 0 to infinity, then say that this is the plot, and when omega is infinity, the magnitude of the plot becomes 0, and it starts in this way when omega is increased for a particular system. Then there are two important things here. One is gain margin. As I said, it is the amount of gain that can be still added to the system without affecting the stability. So, this gain margin is to be determined at phase crossover frequency, that is nothing but omega Pc, and phase margin is the amount of phase angle that can be added to the system without affecting the stability. This phase margin can be determined at gain crossover frequency. So, I can say that the plot consists of 4 parameters. One is gain margin, and the second one is phase margin, and gain margin is determined at phase crossover frequency, and phase margin is determined at omega gain crossover. So, as I am indicating that polar plot is a frequency response plot, how the magnitude and phase angle of the system varies with the omega. So, that is why it is called frequency response plot. Now, if you look at the polar plot, it is crossing minus 180 degrees at some point, say B. So, each and every point on this polar plot will have magnitude as well as phase angle. So, at this point the polar plot is crossing minus 180 degree line. So, this point is called omega Pc, phase crossover frequency. Now, at this phase crossover frequency, if you try to measure the magnitude from this to this, say this is GB, is the magnitude at omega Pc. So, the gain margin is defined as, actually it is 1 by GB, where GB is the magnitude at phase crossover frequency. So, normally the gain margin is expressed in decibels. So, it is 20 log 1 by GB, 20 log 1 by GB, or this can be written as minus 20 log GB, shifting the denominator term to the numerator. So, gain margin in decibels minus 20 log GB. So, if you look at that, the amount of gain at phase crossover frequency, is it less than 1 or greater than 1? To know that, you need to draw a unit circle. It cuts the plot here. So, this is known as unit circle. That means circle with radius 1. So, now if you look at this point, the plot is crossing minus 180 less than 1. The GB is less than 1. So, less than 1. So, if you see the gain margin now in decibels, you will have positive gain margin, because the value of gain at phase crossover is less than 1. So, the gain margin is positive. Now, coming to the phase margin, this phase margin is determined at gain crossover frequency. So, let us say the plot which is being drawn here, polar plot, crossing the unit circle at point A. So, you draw a line from origin through that point and measure the angle in clockwise direction. Draw a line passing through the point A, that is the point where the plot is crossing the unit circle. So, the frequency at this point is known as omega GC, the gain crossover frequency. Suppose the angle is phase angle of the function at this gain crossover phi GC in clockwise direction, then the phase margin is, the formula phase margin is 180 minus the phase angle phi, that is the system phase angle, overall system phase angle. Sometimes this can be written as 180 minus angle of G of S and into H of S. So, this phase margin is positive or negative, that actually depends here what is the value. If you measure, say this is minus 110 or minus 120. So, the phase margin PM is 180 plus the angle that is measured in the clockwise direction. So, that angle I am representing as GH of j omega. So, as long as this angle is less than 180 in clockwise direction, say for example here 180, say this angle is 110 and clockwise direction, so minus, so 110, then you will get 70 degrees as the phase margin. So, for this particular case, both gain margin and phase margin are positive. Both gain margin and phase margin are positive for this particular system. So, we can say that the system is stable. So, the indication is, if you get gain margin of some value in decibels, that gain margin in decibels is positive value. So, you can add that much gain still to the system without affecting the stability, or system may go to the verge of stability. Similarly, phase margin also should be positive for the systems to be stable. Both gain margin and phase margin of the system should be positive for stability. Let us consider the second case from the plot. Suppose the unit circle is drawn with the radius 1. This is called unit circle, means radius 1 with center origin. Now, the plot has this shape. So, this is the plot. Actually, as I said, the omega is increased from 0 to infinity. By the time omega reaches infinity, the plot ends here, means the magnitude becomes 0. So, in this case, if you look at that, the plot is crossing minus 180 degree line here, say this is the point B, and the gain is now from here to here, it is known as GB, and this is a unit circle, so the radius is 1. Now, this is called omega PC, phase crossover frequency. Now, the plot crossing the unit circle at point A, plot crossing the unit circle at point A, if you draw a line through that point, and this point is known as omega GC, gain crossover point, because it is a unit circle whose magnitude is 1. Now, if you try to measure the angle from 0 degree line in clockwise direction, so this phase angle phi at gain crossover point, and omega PC is here, omega GC is here. So, in this case, omega PC is less than omega GC, because you are increasing the frequency. In this particular example, omega PC is less than omega GC, and the magnitude GB is greater than 1 here. The magnitude GB is greater than 1. So, if you see the gain margin 20 log 1 by GB, where GB is greater than 1. So, you will get the gain margin negative in decibels, and phase margin is 180 degrees plus the phase angle of the system in clockwise direction with reference to 0 degrees. So, that phase angle you can look at from here to here, it is greater than minus 180, it is greater than minus 180. So, you have minus say 210 degrees approximately, then you have minus 30 degrees, means phase margin and gain margin and phase margin both are negative here, both are negative. That means system is unstable, system is already unstable, and you have to bring down both the gain margin and phase margin by this much amount, so that system comes to the verge of instability. So, gain margin and phase margin should be positive for stable. Gain margin and phase margin both should be positive for system said to be stable. If you look at another case, that the plot crosses the unit circle as well as minus 180 degree line exactly at this particular point, this way. So, you can see that here omega PC is equal to omega GC, both phase crossover and gain crossover are equal, and the gain margin you can see that GB is exactly equal to 1. So, if you calculate gain margin is the magnitude at omega pc, okay, it is equal to 1 because this is a unit circle. This is a unit circle. So, the gain margin is 20 log 1 by gain, that gain is 1 here. So, it is 0, means there is no margin, there is no margin. Similarly, the phase margin is 180 plus, exactly it is crossing here the unit circle. So, the phase angle is minus 180 if you measure in clockwise direction. So, phase margin also 0. So, both gain margin and phase margin are just zeros. So, we can say that system is marginally stable. System is marginally stable, this one. So, the conclusion is the gain of the system while crossing the 180 degree line should be less than 1 for the system to be stable, and greater than 1 means unstable, and equal to 1 means marginally stable. So, the system loop transfer function is given by g of s into h of s equal to 1 by s into s plus 1 into s plus 2. So, it is a third order system and type 1. Now, for this system you are asked to find out the gain margin and phase margin. So, as I said, this is a type 1 system by seeing the number of poles at origin, and the order of the system is 3 by looking the highest power of s in the denominator, that is characteristic equation. So, in order to find out gain margin and phase margin, we need to draw the plot, polar plot, frequency response plot. So, as s is to be replaced by j omega. So, the function becomes sinusoidal function, it is 1 by j omega plus 1 j omega plus 2, and the magnitude term, the magnitude of the system transfer function is magnitude of g of j omega to h of j omega, it is 1 by omega under root of omega square plus 1 under root of omega square plus 4. So, this is the magnitude function of the sinusoidal transfer function, and the phase angle of the system, g of j omega. So, this phase angle is, you can see that there are 3 terms in the denominator, and the contribution of 1 by j omega is minus 90 degrees minus tan inverse omega for the second term, and minus tan inverse omega by 2 for the third term. You should remember that the loop transfer function is given, and you can find out the stability of closed loop system from this open loop transfer function. So, the procedure to draw the polar plot is, you should know the magnitude and phase angle terms separately. Now, vary the omega, that is frequency, omega is varied now from 0 to infinity, and see that how the magnitude is varying and how the phase angle is varying, and represent all the points in the graph sheet, that becomes polar plot. Now, to determine the gain margin and phase margin, I must know, without drawing the plot, I must know what is gain crossover frequency and phase crossover frequency. So, omega GC and omega PC I must know to determine the gain margin and phase margin. So, for this, as you know that it is a type 1 and order 3 system. So, the plot is like this for the type 1 system, and order 3 system it ends at the origin for omega infinity. Now, you need to equate this angle to know this particular one. This line is minus 180 degree line, minus 180 degree line. So, this point is actually called omega PC. So, to determine omega PC, I must equate the angle term to minus 180. So, what is the angle term here? It is minus 90 minus tan inverse omega minus tan inverse omega by 2. This is the angle contribution of the loop transfer function. So, this must be equated to minus 180, and now you get omega value here. That omega is nothing but omega PC, phase crossover frequency. That helps to determine the gain margin. Now, so when you equate this, you can see now minus 180, you can bring this side, so it becomes plus 180. So, it is 90 degrees is equal to tan inverse omega plus tan inverse omega by 2, tan inverse omega by 2. So, if you apply tan to both sides, tan 90 equal to tan inverse omega plus tan inverse omega by 2, then this can be written as 1 equal to omega plus omega by 2, that is A plus B, by 1 minus product of these two terms omega into omega by 2, that is omega square by 4. So, this can be 3 omega by 2 by 4 minus omega square by 4. So, this is actually equal to tan 90 is sin 90 by cos 90. So, sin 90 is 1 and cos 90 is 0, and if you solve for omega, you will get root 2 radians per second. So, the omega is the frequency, root 2 radians per second you could get by equating the phase angle term to minus 180 degrees. Means the value of omega PC here is root 2 radians per second, root 2 radians per second. Now, if you know this, you can substitute this value, substitute omega equal to omega PC. Now, omega equal to omega PC, that is root 2 radians per second, substitute that in the magnitude term. So, the magnitude term m is equal to 1 by omega is root 2 under root of root 2 whole square, that is 2 plus 1 3 under root of again omega square plus 4, you have 2 plus 4, that is 6. So, you get 1 by root 2 into root 3 into root 6. This magnitude is at omega equal to omega PC, that is to root 2 radians per second. So, this is 1 by root 36, that is 1 by 6. So, this is the magnitude. We were calling this as gain at omega PC. So, the magnitude here is 1 by 6. Now, the gain margin is the inverse of the magnitude at PCF. That way also the gain margin can be defined, that is 1 by 1 by 6, that is 6. So, gain margin is 6, and you can see that the magnitude is here 1 by 6, that is less than 1. The magnitude 1 by 6 is less than 1. So, the gain margin you get positive. So, the gain margin is positive here. So, the system is stable. So, this is the way you should equate the phase angle term to the minus 180 degrees and evolve to find out the phase crossover frequency and substitute that phase crossover frequency in the magnitude term, and inverse of that magnitude term will give you the gain margin. So, let us consider another problem to find out the phase margin. G of s into h of s equal to 1 by s into s plus 1, and find phase margin. And as usual, the procedure to find out the phase margin is to have sinusoidal transfer function, and the magnitude of this function is 1 by omega and omega square plus 1 under root. This is the magnitude term, and the phase angle term is minus 90 for pole at origin, and minus tan inverse omega for the s plus 1 term. So, once you get this magnitude and phase angle, now to determine the phase margin PM. So, the formula for this phase margin is 180 degrees plus the phase angle term of the system at omega equal to omega GC. So, I need to get omega GC. To find out the phase margin. For this, I must equate the magnitude term to 1. So, the magnitude is equal to 1 by omega under root of omega square plus 1 should be equated to 1, and evaluate for omega. So, that omega is nothing but omega GC. So, you can see now it is omega power 4 plus omega square plus 1 equal to 0. Now, just assume that omega square is equal to x, then it is x square plus x plus 1 equal to 0. And if you solve for x, it is minus b plus or minus under root of b square minus 4ac by 2a. A is 1, and this will be 0.718 radians per second. So, if you get x is nothing but omega square, that is nothing but 0.718 radians per second. So, the phase margin is 180, and the phase angle term you can see actually it is minus 90 minus tan inverse omega. So, you can see that in this term there is only one term consists of omega. This omega is nothing but omega GC, that is root of 0.718 radians per second. So, if you substitute that value here, the phase margin you get 52 degrees. So, the phase margin is a positive value you got. So, it all depends on the system parameters. So when you are subtracting from 180 the phase angle contribution of the entire term, if you get a positive value, we can say that the system is stable. So it is a stable system. So the procedure to determine the phase margin is you need to determine the gain crossover frequency. So that gain crossover frequency from the polar plot, we have seen that when you draw a unit circle, where that plot is crossing the unit circle is known as omega GC. So this is the point you should determine and then substitute that omega in the phase angle term to get the phase margin. It is given by 180 minus the phase angle contribution of the whole term and substitute omega equal to omega GC. If you get a positive value, the system is said to be stable. One is giving a system directly and finding out gain margin and phase margin, and from the plot you need not draw the plot, but you can find out phase margin and gain margin by determining gain crossover frequency and phase crossover frequency. You may have the variety of question like this. Here you need to find out the value of K, that is gain constant, which is represented here in the system for a particular phase margin. Phase margin he has given now. You need not determine, but for that phase margin 45 degrees to have, what should be the value of K in the given system. So for this, the function is plus 1. Given loop transfer function consists of the term K. It is called gain constant, and in this case you need to find out that gain constant K for a specific phase margin that is indicated in the problem equal to 45 degrees. So for this I must know the magnitude term of this. It is K by omega under root of omega square plus 1, and the phase angle term is angle GH. It is minus 90 for the pole at origin and minus tan inverse omega for the other term. Now to have the phase margin of 45 degrees, actually the phase margin is given by PM equal to 180 plus the phase angle contribution of the given loop transfer function g of h j omega. So this phase margin he has given in the problem equal to 45 degrees. This is equal to 180 minus 90 minus tan inverse omega. So you can see that this is 90, this is 45. So if we simplify this, minus 45 is equal to minus tan inverse omega. Okay. So the omega you will get as 1 radians per second from this. This omega is nothing but omega GC, the gain crossover frequency. So gain crossover frequency is to be obtained in this manner for a specific phase margin of 45 degrees. Now substitute this omega equal to omega GC equal to 1 radian per second in the magnitude term. In the magnitude term, it is given by K by omega into omega square plus 1. So this magnitude omega GC equal to 1, that is the omega here. So if you substitute here and this equated to 1. So k by omega is 1 now, and omega square plus 1 is root 2, this is equal to 1. So, the value of k is root 2 for a specific phase margin of 45 degrees. So, this is the way the problem may appear to find out the value of k for a specific phase margin of some phase angle. What is the value of A? What is the value of A to get the phase margin of 45 degrees whose g of s into h of s is given by as plus 1 by s square. So, this is another variety of problem that the system has 2 poles at origin and 1 0 at s is equal to minus 1 by a, and the question appears like what is the value of a, that is some constant, to get the specific phase margin of 45 degrees. So, we need to have the phase angle term of this particular system first. So, the phase angle phi is g of j omega, h of j omega is the phase angle term of s square, it is j omega whole square. So, it is minus 180 for this s square term, and for this particular term it is 0 only. So, with plus sign, so it is tan inverse a omega, tan inverse a omega. This is the phase angle term. Now, the specific phase margin is already given, that is 45 degrees, and what is the value of a I need to get. So, you can see the formula for the phase margin Pm, it is equal to 180 minus this term I am writing here, minus 180 plus tan inverse a omega. So, this phase margin is given in the problem, that is equal to 45 degrees, and this is anyway cancel out each other. So, that is equal to tan inverse a omega. So, now if you apply tan 45 is equal to tan of tan inverse a omega. So, you get tan 45 is 1. So, tan of tan inverse a omega is equal to 1. So, omega equal to 1 by a. So, you got the frequency omega equal to 1 by a, that should be substituted in the magnitude term. So, the magnitude is the magnitude of the given function is under root of a omega whole square plus 1 for the numerator term by omega square for the denominator term. So, this magnitude should be equal to 1. You must equate it to 1 to get omega. So, the magnitude condition is the magnitude of the given function should be equated to 1, and substitute the value of omega that we have got equal to 1 by a in this magnitude function. So, this will be under root of a, and in place of omega you write 1 by a whole square plus 1 divided by 1 by a whole square, and this is equated to 1. So, if you simplify this, under root 2 divided by 1 by a whole square is equal to 1, and if you solve for a you get 0.8. So the essence of this particular problem is specific phase margin is given, okay, and that phase margin expression you need to use, and from this you can find out the value of A, that is the constant of the term, and that is equal to 0.8. If the system has phase margin of 60 degrees, the particular system which is shown here, we have two blocks, and this particular system has a phase margin of 60 degrees. So for that specific phase margin, and find the value of K, for gain crossover frequency, that is omega GC, is also mentioned here, 1 radians per second. So if you look at this problem, there is one unknown term in the block, you can see that is K. So we need to find out the value of K for this specific phase margin 60 degrees. And another information is given here, the gain crossover frequency 1 radian per second. So as you can see here, it is slightly different problem compared to the previous problem. The two blocks are in cascade. So the overall the transfer function of this particular system, if you consider that these two blocks are in cascade, that can be treated as G, and this is a unity feedback system, so H is equal to 1. So we can write that G of S into H of S is equal to product of these two terms, K plus 0.366 S by S into S plus 1. So this is the loop transfer function, and as you know that if you want to have a sinusoidal transfer function, it is, we need to replace S by j omega. So K plus 0.366 j omega by j omega into j omega plus 1. So we can write separate terms for magnitude and phase angle for this given function also. Now we need to equate this phase margin term to 60 degrees. From that you have to find out the value of K. So for that I must know the phase angle contribution of this particular system, angle GH is minus 90 for this term, and for this term minus tan inverse omega, and for this numerator term it is plus sign, and tan inverse 0.366 omega by K. This is the phase angle term of the loop transfer function. This I must substitute in the phase margin expression. So the expression for the phase margin is 180 minus 180 plus the phase angle term. So this term I should substitute here, and phase margin is also mentioned in the problem, that is equal to 60 degrees, and it is equal to 180. You can see these terms, minus 90 minus tan inverse omega plus tan inverse 0.366 omega by k. So now you should simplify this. 180 minus 90 is 90. When this 90 comes this side, it becomes minus 90. So you have minus 30 degrees the left hand side, and if you take minus here, tan inverse omega minus tan inverse 0.366 omega by k in the right hand side. So this minus and minus gets cancelled, and you apply tan now both sides. Apply tan, so it becomes tan 30, and this right hand side it becomes tan of the whole term that appears here. So the tan 30 is 1 by root 3, and tan of tan inverse, if you apply, this becomes omega minus 0.366 omega by k by 1 minus 0.366 omega square by k. So here this omega is given, the gain crossover frequency is given as 1 radian per second. You need to substitute here omega equal to omega gc, that is equal to 1 radian per second, and you can get the value of k, the gain constant, as 1.366. So the problem complexity here is there are two blocks that are connected in cascade. So one block you can treat as a compensator to modify the behavior of the system, where the term k is involved. So what should be the value of k, so that you will have a specific phase margin of 60 degrees here with the gain crossover frequency of 1 radian per second. So equating the phase margin term to the phase angle term, substitute here, and phase margin is given, specific phase margin of 60 degrees. So from this, omega value is also given as 1 radian per second. So you can get the value of k as 1.366 for this specific phase margin. So for phase margin of 60 degrees, the value of k is 1.366. That is the idea.